Hello, everyone. Can you hear me?
Yes.
Yep.
עוד פעם יש הד קצת.
Serge, I suggest we start.
Yes.
Yeah.
Sure.
Okay, so welcome back from the breakout rooms. I hope you had fun. So hi everyone. We are very excited to launch the IPC, the Israeli Physics Series of Colloquial Meetings. The IPC initiative really aims to foster the scientific discourse between physicists in Israel and abroad. We were very lucky to be able to bring really extremely distinguished speakers like today's speaker from across the different branches of physics. I'll try to keep this short. You can really find all the details related to the talks on the IPS website. We will send a dedicated announcement before each lecture. Time-wise, talks will be held every other Monday, starting from today. And please log in at 3:55 p.m. for a short virtual get-together on Zoom breakout rooms like today. I hope you had fun. And one last thing, I would really like to thank the organizers who did all the hard work. Chaim from Tel Aviv, Serge from Weizmann, Amos and Yoni from Bar Ilan, Ido from Ariel, Evgeny from Ben Gurion, Yonit from the Hebrew University, and Daniel from the Technion. So without further ado, I'll pass the torch to Avishai, who would give the IPS greetings. Avishai.
Thank you, Snir. My name is Avishai Galyan. I'm the current president of the Israeli Physical Society, the IPS. Myself and the executive committee of the society were very glad to hear of this initiative. I think it's an excellent idea, and we fully support it, and we are very glad to see that it started, and I hope it will continue as successfully. So without taking away from your time, I also want to thank the speaker for agreeing to come to this virtual meeting, and I hope you will all enjoy it. Again, compliments to the organizers for this excellent initiative.
Serge, we cannot hear you.
Serge, you're muted.
Okay, can you hear me now?
Yep.
Yes.
Perfect. All right, so good afternoon, everyone. My name is Serge Rosenblum from the Weizmann Institute, and I'm really excited to introduce today's speaker of the IPC opening session, Professor Pablo Herrero. So Pablo is a professor of physics at MIT. He's the recipient of the Wolf Prize in Physics and of the APS Oliver E. Buckley Condensed Matter Physics Prize, both in 2020. But rather than listing the long list of prizes, let me just share a very brief anecdote. So for me, this is the first time hearing a talk by Pablo, and that's because when I went to the APS March meeting in 2018 in Los Angeles, the hall was so packed that security would not let any more people in. So this earned him the title of physics rock star by nature. And this work that Pablo will present today was also awarded the breakthrough of 2018 by Physics World. So a few notes about the talk. Since there are a lot of people, please do not try to interrupt with questions. There will be time in the middle for a few questions and also 15 minutes at the end of the session. So if you do have a question, please raise your hand or write down the question in the chat, and we will do our best to bring up the question. So without further ado, please, Pablo, go ahead.
Okay. Let me share my screen. Okay. Can you all see my screen?
Yes.
Yes.
Okay, very good. So thank you very much, Serge and Shahal and Eli and everybody who extended a nice invitation to join. As you can see, I'm using a background here, where the place where I should be, where I would like to be, right now. I'm hoping I will be back to Israel very soon. I have so many friends and collaborators there, so I hope this whole pandemic disappears at some point and allows us to all meet in person. So it's really a great pleasure to speak to the whole of the Israeli physics community. I've interacted a lot with the condensed matter community, and I'm glad to be able, to present to the broader community. So I want to tell you about our experiments on Moiré quantum matter. And this is something that, as Serge mentioned, didn't start too long ago, around 2018, although of course we have been working on this a little bit earlier. Now, let me start from a bit more of a general point of view, and let me get my laser pointer here. Okay, so among the most fascinating states of matter that we find in the universe are those where the individual constituents or particles interact very strongly among them. Okay, this is something that occurs in all fields of physics. This is something that you find, for example, in the quark gluon plasma state, which is a state of matter that occurs a few, hundreds of nanoseconds after the Big Bang, and that we can recreate nowadays in heavy ion, accelerators such as, the one at Brookhaven National Laboratory. This is also something that occurs in the different phases of nuclear matter in neutron stars. And this is a picture from the Chandra X-ray Observatory of a neutron star. And if you go to the Wikipedia webpage on nuclear matter, you can see that they have different phases. These phases, very interestingly, they are called, they have a pasta name. So you have the bucatini phase, the lasagna phase, the spaghetti phase. They are very, very interesting in names, and also very interesting physically, where the neutrons interact very strongly with each other. And perhaps a bit closer to my heart, in the different topological states of matter that arise in condensed matter, for example, the fractional quantum Hall state, you also have very unusual behaviors that are due to strong interactions, and where, for example, you can see that particles become fractionalized and all kinds of interesting topological states are present. Now, a large fraction of the condensed matter community is working on strongly correlated quantum materials, okay? And perhaps one of the most famous are the high temperature couplet superconductors, which, exhibit this fascinating behavior, like you can float magnets above them. And they also give rise, these quantum materials, to phase diagrams that, despite decades and decades of work, we have very little understanding about these phase diagrams, okay? I mean, perhaps the most well-known is this D-wave superconductivity here, but there are a multitude of phases that we have very little understanding about. So now, before I go on, and because this is a very general audience, let me just remind you all about what type of behaviors, electronic behaviors, we can have in physics, okay? So from a single particle band theory, okay, simple quantum mechanics tells us that essentially we can divide objects into two categories. One of them are insulators, okay? If you have here the density of states versus energy, and these are the bands in a solid. If one of these bands is completely occupied with electrons, and the next band is completely empty of electrons, okay? There is this band gap here, and this object behaves as an insulator. The reason is that there are no free available states for electrons to be excited onto at small temperature, at low temperatures or at small energies, in order for the material to conduct electricity. Now, the other situation you can have is that one of these bands is completely full, and the next band is actually partially full. Okay, it's not completely full, it's not completely empty, it's partially full. If your Fermi energy is around here, now you have free electron states available for electrons to be excited by temperature or by a bias voltage, and they can therefore conduct electricity. So from single particle point of view, you have either insulators or metals, and it depends on whether you have an electron band partly occupied or fully empty. Now, once you include electron-electron interactions, okay, the situation can become more complex. And in particular, you can have what are known as correlated insulators. So these are systems, okay, where in principle your Fermi energy could be, for example, here in the middle of a single particle band, but due to electron-electron interactions, this band decides to split into two bands, okay? And half of it, okay, one of the split bands is completely full and the other one is completely empty. So now you go to a situation which is similar to this, except that the gap between these two split bands is a gap due to correlations rather than a single particle gap, okay? So these systems are known as correlated insulators. Now, there are a number of correlated insulator systems. One of the most famous is the MOT insulator. The reason why MOT insulators are, among many things, one of the reasons why they're very famous is because they are believed to be the parent compound of high TC cuprate, high critical temperature cuprate superconductors. So cuprate superconductors have these copper oxygen planes. You put one electron in each of these copper atoms, okay? And when you put exactly one electron per copper atom, this leads to an insulated state because electrons now, due to strong interactions, they cannot jump from side to side because double occupancy is penalized, is energetically very unfavorable, okay? However, if you dope with holes, you remove a few electrons, now there are empty sites that electrons can jump onto, and the physics of this is believed to be described by the so-called Hubbard model, which takes into account the penalty of doubly occupying some atoms and the kinetic energy available to hop from one occupied to one unoccupied site. And it is believed that in this correlated motion of empty holes and double occupancy, etc., a very interesting phase diagram appears. Yeah? And I say it is believed because we actually don't know for sure. Okay? Despite more than 30 years of research into high temperature cuprate superconductors and looking at this Hubbard model, this model cannot be solved exactly theoretically, and therefore there's still no one-to-one map between this model and this phase diagram. Okay? So now the difficulty in trying to, in theoretically solving the Hubbard model and trying to understand these quantum materials, and not just in the cuprates, but in more general, electronic interactions in quantum materials, has led to different alternatives, approaches trying to investigate the physics of strong interacting systems, okay? And one of the most novel approaches is to investigate strong correlations in quantum materials by using ultra-cold atom optical lattices, ultra-cold atoms in optical lattices. So already in 2002, Marcus Greiner, then at the group of Emmanuel Bloch, they were able to tune, if you shine lasers at each other, you can create this two-dimensional potential well for atoms. You can load atoms here, like if they were, X in a carton, in an egg recipient, and you can load your atoms, and you can tune the interaction between your atoms using a trick called the Feshbach resonance. And already back then in 2002, they were able to tune the system, the interaction such that the system would result in a MOT insulator or in a superfluid due to attractive interactions. Now, back then this was done with bosonic atoms. So this was a realization of the Bose-Hubbard model. Then a few years later, they were able to do this with fermionic atoms. So this was, they realized the Fermi-Hubbard model. And just to give you an idea, the latest state of the art in ultra-cold atoms is the recent realization of antiferromagnetism in the Fermi-Hubbard model by several groups. Okay, they can look at these atoms and they can see that they go spin up, spin down, spin up, spin down on this lattice. So they have a short-range antiferromagnetism in this Fermi-Hubbard model. So this means that slowly the ultra-cold atoms community is exploring this region of the phase diagram, okay? MOT, antiferromagnetism. They would like to look at the entire phase diagram, and in particular, they would like to look at this region where it is expected that the behavior will lead to D-wave superfluidity due to repulsive interactions. However, it is very difficult for the ultra-cold atoms community to cool down to the necessary temperatures to observe this. In principle, there are no fundamental physics problems to reach this low temperature behavior, but they're very serious technical challenges. They're already working at temperatures of the order of a nanokelvin, and they have to go down into the maybe tens of picokelvin or 100 picokelvin to look at this, and it's taking a large effort. So we have these two platforms to study strongly correlated physics in quantum materials. We have the actual quantum materials. We also have these cold atoms in optical lattices. Yeah. And what I want to tell you about today is about this new platform, magic angle graphene superlattices. Now, as you can see, this platform has a convenient complementary, length scale, between these other two platforms. Quantum materials, the lattice scale, the atomic lattice scale of a few angstroms is the relevant scale. In ultra cold atoms, you have these cold atoms separated by distances of the order of a micron. In magic angle graphene, the superlattice length scale is of the order of 10 nanometers. Associated with these length scales, you have temperature or energy scales. And so in quantum materials, this energy scale is of the order of 100 to 1,000 Kelvin. In cold atoms, it's 0.1 to 1 nanokelvin. Because this length scale is intermediate, the temperature scale is also intermediate of the order of 1 to 10 Kelvin. Okay? So with this introduction, this is what I want to tell you about today. I will describe first a little bit this field of 2D materials, Legoland, and twistronix. You may have heard some of these terms. Then I'll tell you what graphene and magic angle graphene superlattices are. Then I'll tell you about our observation of correlated insulator behavior and superconductivity. And then I hope to have a few minutes to tell you about what has happened since our discovery and some of the latest results. So, already since the isolation in 2004 of graphene, we have been having a lot of fun investigating 2D materials. And in fact, there are many 2D materials, and not only we can investigate graphene, but many others. And soon, the community realized that you can actually put 2D materials on top of each other, stack them on top of each other. And the resulting heterostructure can have very different properties from the individual layers. So this is something that my friends and colleagues wrote reviews about, making analogies between two-dimensional materials and Legoland, okay, and Lego pieces, building structures with Lego. Now, I don't know how many of you have played with Lego. I have small kids, so I play with Lego all the time. And often my small kid, comes and tells me, Daddy, I cannot stack these two pieces of Lego on top of each other. And I have to tell them, look, that's because you're not aligning them perfectly. You have to have 0 degrees alignment between these two pieces of Lego to stack them on top of each other, okay? So although this Legoland aspect of 2D materials is very important, perhaps it's not the most unique aspect, because we also have semiconductor heterostructures grown by molecular beam epitaxy, metallic superlattices, etc. Perhaps the most unique aspect of 2D materials, something that has no history, no precedent in the history of material science, is that we can do this. With 2D materials, we can put two-dimensional crystals on top of each other at an arbitrary angle of rotation that we choose, okay? This is something that you could not do before with bulk material growth or with semiconductor or metallic heterostructures grown by MBE. This is something that we can do now only since we have two-dimensional crystals, okay? So let me stop this before you get dizzy. And let me tell you what we can do with that, yeah? So first of all, our system of choice today is graphene. Graphene is a honeycomb of carbon atoms. So all of these atoms are carbon. They are chemically equivalent. From the crystallographic point of view, graphene has two atoms. We call them A and B, okay? And I'm coloring them here red and green. So you need a two-atom basis to tile a honeycomb. Now, if in a simple tight binding model, using single particle quantum mechanics, you calculate the electronic structure of this system, you can see that it has this very unusual electronic structure where near the Fermi energy, okay, your momentum dispersion, energy momentum dispersion has these Dirac cones, these double cones, okay, which resemble the dispersion of light, okay? So graphene is a zero bandgap semiconductor or a zero bandgap semi-metal. And these Dirac cones, have received a lot of attention, and there are all kinds of analogies with massless ultra-relativistic particles. Starting with the fact that if you actually write down what's the Hamiltonian equation for the system, you see that this is the Dirac equation in 2 dimensions for massless particles. Okay, energy is proportional to momentum. Now, in the Dirac equation, this spinor actually tells you whether the electron spin has spin up or spin down. In the case of graphene, this is a pseudo spinor, which is telling you whether the wave function, the electron wave function, is on the A sublattice or on the B sublattice. Okay. Now this is the only equation that I'm going to show in the entire talk, so no worries. Now, the other thing that is important to know about graphene is that there are two inequivalent valleys, we call them, these double Dirac cones. These are the K and K prime valleys in momentum space. So electrons in graphene have these fourfold degeneracy, or they have these 4 degrees of freedom: spin up, spin down, valley K prime. Just remember 4, the number 4, it will appear later. Okay? Now, what happens if you put in real space graphene on top of graphene and you vary the angle? A moire pattern forms, okay? This superperiodic pattern that you can see here, these soccer balls, and the distance between these soccer balls, these moire wavelengths, depends on the twist angle. It can reach all the way to infinity because these are 2 identical lattices, okay? So again, let me stop this. Now, that's what happens in real space. Let's look at what happens in momentum space and therefore to the energetics of the system and in the electronic structure. So if we have here graphene, this is the energy momentum dispersion, this is the reciprocal space, this is a Dirac cone, okay? And if you have your Fermi energy above this Dirac point, you have this Fermi disk at the corners of the Brillouin zone, okay? K and K prime. So now, if you put another graphene sheet on top and it's perfectly aligned to it, then the reciprocal spaces are perfectly aligned. The Dirac cones are on top of each other, okay? Now, what happens if you now rotate in real space? Well, in reciprocal space, the Brillouin zone also gets rotated, okay? So rotation in real space leads to separation in momentum space, and the separation between these Dirac cones is proportional to the sine of half the rotation angle, okay? So twisting leads to layered Dirac cones separating in momentum space. Now, let's start from a small rotation angle such that the difference in momentum is proportional to the angle, because sine of a small angle is equal to the angle, okay? And let's see what happens. So now this would be the situation, okay, that would occur in the energy momentum dispersion for small angles, so that the separation between these points is proportional to the angle. But this would be the situation if electrons in one graphene sheet would not know about electrons in the other graphene sheet. However, electrons, these 2 graphene sheets are just 3 angstroms apart. So the electrons in one sheet are very much able to tunnel to the other sheet, okay? So this tunneling leads to hybridization. It leads to bonding, anti-bonding type of energy states, similar to a hydrogen molecule, where you have bonding, anti-bonding molecular states. So you have a, this interlayer interaction or tunneling, you have a gap that opens here at this crossing point. Yeah? Now, the situation occurs when this gap is much smaller than BFK theta. Okay? If you now decrease the twist angle, you can see that these 2 cones, these 2 crossing points will get closer and closer to each other, and this bonding state will get lower and lower in energy until you reach a condition where that lower band goes down to 0. You reach something which is known as the flat band condition, okay? This flat band condition is reached at the so-called magic angle, and famously now it was famously then, but now very famously, Rafi Bistritzer and Alan McDonald predicted this magic angle to be 1.1 degrees back in 2011, okay? And there was also interesting simultaneous experimental and theoretical work at the time. Now, this is a magic angle for graphene on top of graphene. This depends on the materials. Yeah? Now, this is sort of a schematic. Let me show you an actual calculation. This is an actual calculation of energy versus momentum for magic angle graphene. Okay? These are the set of flat bands. And there are another set of remote bands. Each of these are called moire mini bands, okay? Due to the periodicity of the moire wavelength, you break up your energy momentum structure into a set of mini bands. In this case, spaced by band gaps from the flat bands to the more remote bands. These flat bands are the ones that we're interested in, okay? So now, we have now this picture in momentum space, we have these flat bands, okay? How does this look like in real space? Okay? let's try to go back. If the electrons are in these flat bands, how will the electron density look in real space? Remember, to go back between real space and momentum space, you have to use a Fourier transform. So the Fourier transform of a flat thing, okay, is actually a delta function. So these bands are not 100% flat. They have a little bit of dispersion, but they are much, much flatter than the original graphene dispersion, okay? So when you do the Fourier transform, you can see that the charge density, the electrons in graphene, they like to be in these regions, okay, which are locally, the two graphene sheets are on top of each other. So these regions are called of AA stacking, where every carbon atom is locally on top of every carbon atom in the bottom sheet. These regions are separated by these AB and BA stacking regions, where the lattices are, because it's a small twist angle, they are locally shifted with respect to each other, okay? So from the top, and schematically, we have now a moire superlattice, which has regions of AA stacking, where the electrons like to sit, and regions of AB and BA stacking, where the electrons don't like to sit. And these are separated by BA-AB domains, okay? From a slightly more realistic schematic, this is what this looks like, okay? We have these regions of AA stacking. These are separated about 13 nanometers. This is what's going to form our triangular Fermi-Hubbard lattice where electrons are going to like to sit, okay? I put in quotes triangular because in reality, this is also a honeycomb lattice because these AB and BA regions are not identical. So they form, this is actually a honeycomb lattice with plaquettes. Now, let me start telling you, showing you some experimental data. So this, we make devices, and you can ask me later how we make our devices. Quite interesting if you're curious. But we make devices where we have the twisted bilayer graphene on top of each other at a small angle, okay, 1.1 degrees, for example. And these devices are sandwiched. They're encapsulated by two crystals of hexagonal boron nitride, which is a very high quality insulator. And then they're contacted by source and drain electrodes so that we can apply a voltage and run a current through the graphene system, through the twisted bilayer graphene system. And we also have, interestingly, a metallic electrode, which acts as a gate so that the whole geometry is that of a field effect transistor geometry. With this gate, we can change the density of electrons in the twisted bilayer graphene by applying a gate voltage, by applying an electric field. Okay, so just as a reminder, what happens if you only had one layer of graphene, not twisted bilayer graphene, but just one layer of graphene? Okay, if you measure the conductivity versus density for one graphene layer of graphene, you have this V-shaped behavior. Okay, if your Fermi level is deep into the valence band, you have lots of holes, so you conduct very well. If your Fermi level is deep into the conduction band, you have lots of electrons, so you conduct electricity very well. If your Fermi energy is at charge neutrality or at the Dirac point, you have very few charge carriers, so you conduct poorly. So the conductivity of regular graphene versus charge density or gate voltage is this V shape, okay? And this has been seen by thousands and thousands of groups now. Let me show you what happens when you measure magic angle graphene. So these are measurements of the conductance versus charge density. This charge density is in units of 10 to the 12 electrons per square centimeter, okay, because it's two-dimensional. And this is a conductance in millisiemens. So in order to understand the way this looks, you can see this V shape near zero, near charge neutrality. That looks like regular graphene. But then you can see all kinds of crazy things, okay? So let me remind you, this is the electronic structure of the system. So these flat bands can take up to 8 electrons per more unit cell. Or in other words, we can go from totally emptying the flat band, meaning we have 4 holes per more unit cell, or we totally fill the band and there we have 4 electrons per more unit cell. Remember, this number 4, I told you that it would appear again, okay? So when the Fermi level, with the chemical potential of our system is here in the gap between the flat bands and the remote band, we are here in conductance. We have 4 holes per more unit cell. Our chemical potential is at a band gap. So the system is an insulator, does not conduct electricity. We can shift with our gate voltage, our chemical potential to be here in the middle of this other band gap. That corresponds to filling 4 electrons per more unit cell. This is also single particle insulator. That's why it doesn't conduct electricity. Now, the funny thing is that if we put now our chemical potential, our Fermi energy here in the middle of the valence band, the system is crossing this, the Fermi energy is crossing this band. We should have a good metal in there. However, when we put 2 holes per more unit cell, we have an insulator. This turns out to be actually a correlated insulator, okay, as I mentioned earlier. If we shift the Fermi energy to put it in the middle of the conduction, of the flat conduction band, we also see an insulated state. This is at 2 electrons per more unit cell, another correlated insulated state. The systems should be a metal when we put these number of electrons or holes, and it's not, it is an insulator, okay? And this behavior, interestingly, is only observed when the angle between these 2 graphene sheets is very close to this magic angle. Only in a small angular range between about 1 degree and 1.2 degrees, this behavior happens. You can say that the magic only happens roughly between that 1 and 1.2 degrees, okay? Now, this insulator has very interesting properties, in particular in a magnetic field, etc. I don't have time to tell you now all of the details, but please don't hesitate to ask me questions, and I encourage you to read the paper if you haven't looked at it. Now, so let me tell you, let's look a little bit closer, at this uncorrelated insulator behavior. So here's again the same data that I just showed you, okay? This NS is the superlattice density of 4 electrons per more unit cell. NS over 2 means 2 electrons per more unit cell. We call at the time this half filling. This is half filling of holes. This is full filling of holes. That's why the negative sign. Now, as we were looking at these data, we were doing, temperature dependence, okay? And then when we were looking at the temperature dependence of the conductance here around the correlated insulator for electrons, we saw that, these are traces at different temperatures from 1.7 Kelvin to 0.3 Kelvin. We saw that the colder we went, the lower the conductance was. Now, that is what is expected of an insulator. When you cool down an insulator, it conducts less and less the colder you go, because there's less and less thermal energy for electrons to get activated across the band gap, okay? So that's normal insulator behavior. When we look around the correlated insulator state for holes, for 2 holes per more unit cell, the insulator state itself also behaved like that. However, right next to it, we saw this conductance enhancement as we went down to lower and lower temperature. So we found that very, very curious, So I remember when my students asked me, they said like, what should we do? Should we make more devices and in a 4-terminal geometry to see how well this wants to conduct, okay? Now the thing is, this data have been taken in a geometry where we had only 2 terminals, source and drain, attached to the graphene. And that is because if you're looking for an insulator state, which is what we were looking at the time, okay, you can do 2-terminal geometry measurements. This introduces a small series resistance with your device, but if you're going to measure infinite resistance, adding some small resistance, who cares? However, if you want to see if something conducts very well, you don't want to have that series resistance in series, okay? So what we did is we made devices in a 4-terminal geometry. Okay, same type of fabrication, graphene on graphene with a small angle. And then we can now have source and drain electrodes and independent voltage measurement probes so that we can measure within the graphene and see if there is any resistance there at all, okay? And this is data for another device. This is 1.16 degrees. These are the data with a small perpendicular magnetic field applied to it. You can see these are also data in 2-terminal conductance so that we can first characterize them in a 2-terminal conductance because it's simpler, okay? So you see there is this V shape near charge neutrality. You have insulated state at 4 electrons and 4 holes per more unit cell. You have also dips in conductance at 2 electrons, 2 holes per more unit cell. Other stuff happens at 3 holes and 3 electrons. There's a lot more stuff going on here that I'm not telling you about. But the important thing is, if we now remove the magnetic field, you can see that not too much happened here, but here a lot of stuff happens. Okay. Well, now we change to our 4-terminal geometry measurements so that we can measure exactly how well this wants to conduct. And what, to our surprise, what we saw is that magic angle twisted bilayer graphene superconducts. Okay, if you measure the resistivity or the resistance as a function of temperature, you have this dropped, by several orders of magnitude below our noise measurement floor. These are data for 2 samples. We have by now measured many samples. Okay, and magic angle graphene is a 2-dimensional superconductor. Okay, now you can do any, you can look at any measure of a 2-dimensional superconductivity that you want. For example, you can measure the VI curves. You see, you can run a current through magic angle graphene without any voltage dissipation, okay, until the critical current. This is perfectly 2-dimensional superconductivity. Now, the nice thing, as I told you earlier, is that we can vary the density of electrons in our system. So what we saw is that if you look at varying the charge density around this region, and you look now at the resistivity as a function of temperature and charge density, you have this at 2 holes per more unit cell, you have this correlated insulator behavior. And then as you go dope with more holes, you have a superconducting dome. Blue means superconductivity, okay? As you dope with electrons, you have another superconducting dome, okay? So when my students showed me this, I was really surprised and fascinated, because this reminded me very much of the hundreds of times I had seen phase diagrams such as this. Okay, this is temperature and doping for the high temperature cuprate superconductor family. Now they get the doping in the wrong direction. Let me just flip it for you. Now it's correct. Okay, so 0 doping means 1 electron per copper site in the cuprates. It's a mode insulator. If you dope with holes, you have a big superconducting dome. If you dope with electrons, you have a small superconducting dome. Here in magic angle graphene, we have this correlated insulator state at 2 holes per more unit cell. If you dope with extra holes, you get a superconducting dome. If you dope with electrons, you get another superconducting dome. Now, of course, the difference between these 2 plots, I mean, there are many differences, okay? But from the experimentally, one key difference is the fact that this is a theoretical diagram, phase diagram, okay? Experimentally, to build this phase diagram, you need to grow hundreds of crystals, each with different chemistry, often each with different even elements and compositions, okay? Because you cannot grow all materials or dope them, for holes, for electrons, and in all the doping ranges. So to build this phase diagram took thousands of growths by many crystal growers, growing different materials classes with different dopings. Here, this phase diagram, it's in a single device, realized electrostatically, and it takes us a few seconds to go from here to here and measure this entire thing. It takes only a few hours, okay? So that's a big difference in between these 2 systems. There are other differences, okay? The analogy only goes so far. Now, these are, data for another device, 1.05 degrees with a higher TC. This one is a maximum TC of the order of 1.7 Kelvin. More often than not, we see this big asymmetric behavior between the dome for electrons and for holes, okay? This was sort of the most parallel, the most symmetric we have seen it. Typically, the superconducting dome for holes is much bigger than for electrons. Now, I showed you this data, right? And the TC is of the order of a Kelvin. Actually, the latest devices, the best devices is of order 3 Kelvin, something like that. So how strong a superconductor is magic angle twisted bilayer graphene, right? I mean, on one hand, you could say, well, what's the big deal? 1 Kelvin compared to the cuprates, which is 100 Kelvin or so, okay? But, physicists do not compare strength of a superconductor just based on TC. TC is very important, if nothing else, is, for applications. But the way you compare superconductors is by comparing how high is TC, even how many electrons can contribute to the superconductivity in your system. Okay? This is something that it's usually shown in this log-log plot called an Uemura plot, where you have on one axis the critical temperature, and on the other axis the Fermi temperature in Kelvin, okay, which is basically the density of electrons, divided by some effective mass and some degeneracy, okay? And I have normalized here so that you can put two-dimensional and three-dimensional systems in the same plot. Now, in this Uemura plot, BCS weak coupling superconductors, okay, standard BCS superconductors are in this corner, okay? For example, take aluminum. Aluminum has a TC of 1 Kelvin, okay, but a Fermi temperature of over 100,000 Kelvin. Aluminum has a gigantic amount of electrons that can contribute to superconductivity. Given how many electrons aluminum has available to contribute to superconductivity, its TC, it's very, very modest, okay? This is the weak coupling regime. The more you go diagonally in this direction, the more strongly coupled and the more exotic the superconductivity becomes, okay? And in particular, in this purple band, you have pretty much all of the unconventional superconductors. Yeah? You have here the cuprates, you have here the iron pnictides, you have here the heavy fermions, you have the organics, okay? I have even included data here for ultra cold atom lattices where they can reach all the way to the VEC, VCS crossover, to the unitary limit, okay? Where is the strongest couple, most strongly coupled you can be, yeah? Now, where is magic angle graphene in this diagram? Okay, it's here, okay? It turns out magic angle graphene has a very high TC, okay, of the order of, between 1 and 3 Kelvin, and an extremely small amount of electrons, density of electrons, okay? In fact, magic angle graphene is the lowest density two-dimensional superconductor by over an order of magnitude with respect to the next, okay? So the system has an extremely strong coupling, which makes it very difficult that the system could be described by BCS weak coupling superconductivity, okay? This needs to be still resolved, okay? But it makes it very, very unlikely. Now, many key questions remain, okay, even to this day. And in particular, one that many people ask is, what is the origin of these correlated insulator states and what is the superconducting order parameter, okay? And now, here I'm listing just a very, very small list, okay, of theoretical papers that were posted within weeks of us publishing our paper, okay? Now, I stopped updating this like 2 weeks or 3 weeks after our paper, okay? But now there are literally thousands of these papers. The first one was by Senke Xu and Leo Valens at UCSB in Santa Barbara. They proposed some, D plus ID chiral topological superconductivity, and then they have many others. I don't want to talk too much about, basically you have, in terms of order parameter, all of the letters of the alphabet have been predicted, S wave, D wave, P wave, F, S plus P, S plus D, you name it, pretty much everything has been predicted. I don't want to, choose a particular one, we don't know yet. I want to talk only about this second paper, by Volovic, which was an interesting one. So Gregory Volovic is a distinguished condensed matter theorist working in Finland, and he sent us an email, a week or so after we posted our results, and in this email he told us, dear Pablo, thank you very much. You have finally realized everything I predicted theoretically, So, some of you may be laughing. Actually, the surprise was not that email. We got a lot of emails from theorists telling us that, okay? Everyone had predicted this thing apparently, or had an interesting prediction for this. The interesting thing is that if you actually look at the paper, the following thing happens. Already in 2013 or something like that, okay? 7 or 8 years ago, 5 years earlier, Volovic had written a paper analyzing the following experimental situation. It turns out for many decades, going back to the 60s, okay, or even the 50s, there have been about once or twice per decade experimental reports of very high temperature superconductivity in graphite, okay, including room temperature. Now, Bolovic said, this is too many reports for it to be really not true, okay? I tell you what's going on. All of these experiments have been done using graphite, which was turbostratic graphite. Graphite where there are small misorientations between the graphene planes in the graphite. If you have these small misorientations between the graphene planes, then you are going to have flat bands and a strong coupling superconductivity with very high TC. So in this paper that I mentioned here, he said, you see, someone has finally made the control experiment, just two planes, small angle, you see flat bands, strongly coupled superconductivity, very high TC to TF ratio. Now just keep going, stack a few more layers until you get to room temperature. Come on, get working on it, okay? So, I used to think those experiments on graphite were like, kind of crazy. Well, now I don't know, who knows? Maybe this is the route. We'll see, okay? Some people are trying. So now, I want to tell you about the latest and outlook, but I was told that I should ask you all for, briefly pause to see if there were any questions before I continue with the latest and outlook. Such, are there any questions or anyone? Are there any questions?
Yes, I would like to ask, do you really understand this flat direction? They correspond to some symmetry. It reminds one of Goldstone bosons. What are they? And a second related question, did people try to write down some kind of Landau-Ginzburg model for this system?
So let me see. So in terms of why there is
flat direction?
Yeah, so in terms of, no, it's not a given direction that the bands are flat. This is in the entirety.
So even more so.
Yes, exactly. So I have an animation that let me see if I can get my cursor here, because this will allow me to show an animation, which I didn't show, but I was hoping I would get a question so that I could show it. So this is good. Let me show, this is an actual calculation as a function of angle, okay? Rotation angle. You can see the angle is decreasing. This you can see in the entire 2D, okay? The dispersion, you can see that at 1.1 degrees, this is going to become flat in all directions, very flat there, okay? So this is something, it's not a particular direction, it's everywhere. This is the snapshot at 105 degrees. This is flat everywhere in momentum space, okay? So it's a special condition where your electrons basically are as comfortable going through one graphene sheet as tunneling to the other graphene sheet, okay? When that tunneling becomes as good as going through your own graphene sheet, that flat band condition takes place, okay? At a deeper level, people believe that this has interesting connection with topology, okay? Which theorists are still working out the details, okay? But some people believe that at the core of this is an interesting topological physics that occurs because of the special Dirac cones of graphene, okay? Now, you told me your second question was about trying to have a Landau, a Ginzburg-Landau model.
Yeah, some effective description of all of these phenomena. Can you write down some effective theory which?
So you can make, you can use Landau-Ginzburg paradigm to extract several things about the system, including in the magnetic field behavior. What is the superconducting coherence length and all kinds of things like that. Okay, I think that people are trying, for the majority of the theories, they're trying to take to. Some people, a minority, but some people are still trying to describe it by BCS theory of superconductivity by increasing the coupling strength. It's called strong coupling BCS, okay? And then the rest of people are trying to basically start from a model of interacting electrons in a lattice, okay? And you can go at it from weak coupling, and then you try to see what type of phenomenology you can describe, or you can try to start from the ultra strong coupling. It turns out this system is in the intermediate coupling regime, where the interaction energy and the kinetic energy are of similar order, okay? It's not like 100 times one larger than the other or the other larger than the one, okay? And that intermediate coupling regime is the hardest actually theoretically to calculate. Yeah? So that's where people are, and that's why so much theory work going on, and still people are confused.
Okay.
Hi, Pablo. Can I do my question now or just
Sure.
in the end of your presentation?
Maybe one more question, and then I can keep going, and then I'll.
So, thank you. Look, could you go back to your slide when you showed the proximity between the superconducting dome? Because actually, you started to answer my question when you showed your graph tuning the angle, the metric angle.
Okay,
right?
tell me.
Right. But I would like to ask you, how the metric angle govern the proximity between the superconducting dome?
Okay, so what happens is that the observation of superconductivity and correlated insulator behavior occurs mostly in a narrow range of angles around 1.1 degree. Okay, so basically between 0.9, 0.95 and 1.2 degrees, if the angle is there, then you observe this, typically the superconductivity and correlated insulator behavior. If the angle is off by more, you do not observe this behavior, okay? So that's what governs, the appearance of superconductivity.
So there is some mathematical expression that tells us how the superconductor dome will approximate it in terms of the metric angle?
No, that thing does not exist yet. No one has calculated TC as a function of angle, so to speak. No, that thing doesn't exist. We have experimental data. We know how the maximum TC changes with angle. By now we have a superconducting dome in angle rather than in density, okay? But there's no theory yet for all of this. Okay, so maybe let me, I suggest I continue because I have only a few minutes, and I tell you something a little bit about the latest, and then we can continue with more questions. Okay, so let me tell you what has happened since our discovery. Okay, so we published this in April 2018. What has happened there since then? The first thing is that we have reproduced our own results. Believe it or not, that doesn't always happen. So it's good when you're able to reproduce yourself. So we have since then made many, many more devices. Here is what I told you before. This is TC as a function of twist angle. And we sort of have a superconducting dome between 0.9 and 1.2 degrees. Okay. More important than you reproducing your own results is when other people reproduce your results. Okay. So by now, many groups have independently reproduced our results and extended them to other systems and in interesting directions. Okay. The first two papers to reproduce our results were by the group of Corey Dean and Andrea Young, where they were able to reproduce our results and tune the superconductivity also with pressure. And the second report was by the group of Dmitry Efretov, who saw additional superconducting domes, and a richer phase diagram. Another thing, that we have seen, and I'm only going to list here, we have seen linear resistivity behavior, which is reminiscent of the strange metal and Planckian physics that takes place in many correlated materials. We have measured anisotropies in the critical magnetic field and critical current, which are indications of nematicity, spontaneous breaking of rotational symmetry in the superconducting state of the system. We have looked at other systems, for example, magic angle twisted bilayer graphene, so 4 layers twisted pairwise on top of each other. They have very interesting correlated physics. A lot of scanning probe microscopy studies, first STM has happened. I'm very happy to tell you here, and I hope Eli and Shahal will be tell you about this in future talks, but I have very, very fruitful collaborations with physicists in Israel. In particular, a group of Eli Seldov has developed this extremely sensitive technique, putting a superconducting quantum interference device on a tip that they can scan on top of our magic angle graphene devices. That tip is very sensitive to magnetic fields, so they can look at the twist angle, locally the twist angle in our system, and we can see that these systems, magic angle graphene on top of graphene, the overall angle is this magic angle 1.1, but it has small angular misalignments of the order of 0.01 degrees or so, okay, in each domains. And Ellie was able to map it. This was the first direct demonstration of this. And we published this very nice paper. With the group of Shahal Ilani, we looked at different scanning technique. It was scanning single electron transistor that his group has developed. And similarly, we can scan on top of our magic and graphene devices. And we can look at different angles, and we can look at something known as the compressibility. Okay, basically it's telling you what the chemical potential in your system and its variation with density is. And we measure, we see that at each of these integers, okay, at 1 electron, 2 electrons, 3 electrons per mole unit cell, we have this sawtooth behavior indicating a cascade of phase transitions. And that is helping us a lot understand the system. I have to say that this paper was published on my birthday, which was also the day I was supposed to receive the Wolf Prize at the Israeli parliament ceremony. Unfortunately, I couldn't do it. Maybe it will be on my birthday next year. We'll see how it goes. I should mention this was also published. There was simultaneous work by the group of Ali Jizdani reporting very similar results. And another thing which is very remarkable is that ferromagnetism, anomalous Hall, and quantum anomalous Hall physics, that means topology, has been discovered in the system. Okay? There was, in fact, this correlated Moiré superlattices are merging 3 of the most active areas of condensed matter physics. You know, the 2D van der Waals materials community, strongly correlated materials, and the topological condensed matter physics community, they all come together in this field of correlated Moiré heterostructures, okay? So there was a, you know, with my collaborators, we predicted that indeed there would be topological, you know, bands in these Moiré superlattices. There was a lot of extra theoretical work. And soon after, the group of David Gohaber-Gordon reported this large anomalous Hall effect, okay, in magic angle graphene aligned to hexagonal boron nitride. When you align the magic angle graphene lattice to the underlying lattice, you break a symmetry of the system and you get this ferromagnetism. And a few months later, the group of Andrea Young, they demonstrated the quantized anomalous Hall effect in the system, okay, making it clear that the system has very interesting topology. So as you can see, more quantum matter has sort of a little bit of magic. So many things happen, okay? You can have correlated insulators. These have been seen in many, many more heterostructures, not just magic and graphene. You can see superconductivity. It has been seen robustly only in magic angle graphene, but there are some indications in others. They still need to be reproduced. You have topological phases, such as this quantum anomalous Hall, etc. You have magnetism. You have nematicity. Now, why stop there? Maybe we can actually find all phases of condensed matter physics in these systems, okay? In particular, what about Moiré ferroelectricity? Is another emblematic phase, similar to ferromagnetism, okay? Well, as of 2 weeks ago, there were 3 papers, including a very nice paper by Moshe Ben Shalom, Tel Aviv University, where we all, my group and these 2 other groups, they showed that indeed you can have Moiré ferroelectricity in the system. By putting materials which are not ferroelectric together, you can engineer ferroelectricity in the system, okay? And this is because, again, we can do something very interesting with these 2D materials. If you take hexagonal boron nitride, the substrate that we put our graphene devices on, the natural stacking, it's also a honeycomb lattice, and the natural stacking is AA prime, boron atoms on top of nitrogen atoms. But if you take a monolayer of boron nitride, you break it in 2 pieces and you stack it on top, now all of the atoms are on top of themselves, okay? The spiral stack bilayer HBN is non-centrosymmetric, and that allows you, that's very uncomfortable for the system, so the system decides to go into these AB and BA stacking configurations, which have finite electric dipole moment that can be switched with an electric field. So this turns into a ferroelectric, okay? We can make ferroelectric field effect transistors based on this. I'm gonna go fast because I'm running out of time, but just show you that you can indeed, by putting a graphene sheet on top of this parallel stack HBN, you can see you sweep in one direction or the other, and you make a ferroelectric field effect transistor. This is the world's thinnest ferroelectric, less than 1 nanometer in thickness, okay? You can also make a small angle rather than parallel stacking, and you make a Moiré ferroelectric that you can switch with electric field. These are the data showing that switching. Let me skip it. I will be happy to answer questions if you want. The interesting thing is that all of this is working at room temperature, okay? So we have the world's thinnest ferroelectric, and there are very few two-dimensional ferroelectrics, and it works at room temperature 100%. Okay, so this is something that we're very excited, and there's a lot more to come in this area. So with this, I want to just conclude by reminding you, this field of correlated Moiré heterostructures is very rich. It has brought together many condensed matter physics communities, and even the atomic physics community is very curious about these systems. And I want to end by perhaps the most important slide, which is to thank all my collaborators, in particular my grad students, Yuan Sao, Danielle, Jane, Vala, Jason, etc., that made the magic angle graphene. Kenji and Shirui did the two-dimensional Moiré ferroelectricity, and of course lots of collaborators, and especially my collaborators are Weissman, Shoal Ilani and Eli Soldov, for a very fruitful ongoing collaboration. And I want to thank you all for your attention.
Thank you, Pablo, for this fascinating talk. So we have about 10 minutes for more questions. Please raise your hand if you do have one. And I think we can start with Naomi Oppenheimer.
Thank you for the great talk. Yeah, my name is Matan. Sorry, we're taking this Zoom together. I have a question about the devices. So once you make a device and you stack 2 layers together, and you make a twist, this structure as a whole is chiral. So what does breaking chirality, what role does it play in all this new physics that you discover?
That's a very interesting question. Okay, indeed. You can rotate by theta or by minus theta, and it will have different chirality, right? Indeed. In principle, the electronic structure should be symmetric when you do theta and minus theta. But now, there are interesting theoretical predictions about what happens if you go on. Let's try 3 layers. So you can make now theta, theta, or theta minus theta, okay? One is chiral, the other one is not. And those have actually vastly different properties. So this is just the beginning. I talk about 2 layers, but theorists are now calculating what happens when you do 3, 4, 5, 6, all numbers of layers with all kinds of angles in between and so on. So it's extremely rich, and we have a lot of things to do. And experimentally, almost nothing is known about that. The fact that this structure is chiral and the symmetries that breaks actually has other nonlinear phenomena that make possible several nonlinear phenomena, something, for example, called as nonlinear Hall effect possible. And there's a lot of very interesting physics that has been predicted for other systems, which now turns out to be present also in the system because it breaks similar symmetries, with the addition of having all these correlations on top of it, okay? So it's actually very rich. Very little is known experimentally because it's pretty young, the field, but a lot of groups are working on this.
Thank you.
Yes, Marek Karliner. And also, by the way, I want to encourage students to ask questions, please.
Please.
Are there other interesting systems where you can study Moir's heterostructures on different distance scales? For example, you mentioned at the beginning of your talk using lasers to generate a one-dimensional lattice. Can you use lasers to generate 2 lattices which are rotated with respect to each other?
Very good question. Indeed, this has been already the theoretical, the ultra-cold atoms community is actually, they were quite surprised by this. And they said like, oh, we can do that. We can also put lasers and put 2 layers and rotate them. Okay, so the theory community started to also make predictions about how to make this with ultra-cold atom lattices by having 2 lattices rotated. So they have predicted similar conditions for flat bands. And now experiments have to do it. Experimentally, it's a lot harder to do these 2 lattices and rotate them the way they have their laser systems. Now, theory group, the group of Maciek Lewenstein, has actually posted the papers. The advantage of the ultra-cold atoms community is that they have absolute 100% control over their degrees of freedom with the lasers. So what they say is like, you actually don't need to have the lattice rotated if you have lasers, because we can recreate, you can simulate that effect of rotation, which is just modulating the hopping between the 2 lattices by putting appropriate phases in your lasers, okay? So by adding appropriate phases in your lasers, you can modulate that hopping so that even with parallel two-dimensional layers, you can recreate those flat band conditions at that magic angle physics. Okay? So the cold atoms community is very interested in this, but their apparatuses take years and years to put together. So there's a lot of inertia there. Now telling them, oh, just add 20 more lasers and do this and that takes some time. So I think it will take them a little bit of time to jump into it. I think they are looking at what we're doing in condensed matter to see when is the right moment to invest, make those infrastructure investments.
Thank you.
Any other questions? Yes, Jonathan.
Yes, so I'd like to ask about this ferroelectric physics in more bands. Do you see prospects in tuning ferroelectric quantum critical point continuously in these systems?
So very interesting. So in the structure that I showed, this twisted, either parallel stack or hexagonal boronotride, okay, there is always an electric dipole moment. Yeah, you can switch it with an electric field, but we don't have something tuned there so that the ferroelectricity can disappear and you can reach the quantum critical point between having ferroelectricity and not having it. Okay? But I believe there are the structures where this could happen, or by playing perhaps with, there are structure types where you can compensate and make the structure centrosymmetric or not by applying strain or rotating the angles, in situ. Okay, nobody has done that, but in principle it's possible. I would be very interested to see, indeed, if we can reach a ferroelectric quantum critical point. I think that, to me, one of the most attractive things, in addition to the ferroelectricity itself, is what you can induce with this ferroelectric order, which is on a Moore lattice, in other systems also. Okay, so that will be also very nice to.
Yeah, systems with the spin orbit coupling could be very
For
interesting.
example, indeed, for example.
Fred, please.
Yeah, I wanted to ask if by now there is enough evidence to tell what is the order parameter, what is the symmetry of the order parameter? Is it is there any evidence for something topological or?
So we do not know. The type of measurements that, for example, were done in the cuprettes to demonstrate D wave, right? ARPES or phase sensitive measurements in a squid geometry. Those are much harder to do for magic angle graphene. Okay, ARPES, the flat bands have such a small bandwidth that is below the resolution of ARPES to see the details of the electronic structure. Okay, so we need improvements in ARPES, both in temperature and energy resolution to see. And I hope that in the same way that cuprettes stimulated development in ARPES techniques to measure, their properties, magic angle graphene will push the frontier of energy resolution and temperature to measure the bands. Already a few papers have appeared where they have a few pixels in the flat bands and they can see the flat bands, but it's a few pixels. They cannot look at details. Yeah. Now, for phase sensitive measurements, in the cuprettes, you could cut the cuprettes along a crystal facet, 2 crystal facets, and put an S-wave superconductor on either crystal facet and do these phase sensitive measurements. Because magic angle graphene is 2D, the equivalent of having 2 crystal facets. We don't have a vertical facet we can slap a superconductor onto. We have an edge, and that edge making contact in a tunneling with momentum conserved, along the, perpendicular to the boundary, etc. It's much harder. A number of groups are trying those experiments, but there are no results yet. I have heard rumors, I can't disclose from where or how, where people have told me, someone has already some indications there is non-S-wave, the order parameter, but I can't comment more on it. It's just rumors, and I prefer not to tell.
Okay, thank you.
So we have time for 2 more quick questions. So let's start with Benjamin.
Hi, Pablo. Thank you for that talk. So 2 sub-questions. So One is, I would expect graphene to be a prototypical particle hole symmetric material. So is there any like fundamental explanation why we see a very different behavior when you dope with electrons or with holes? The other part of the question is, one of the aspects people look, as I've seen in these Moiré superstructures, is excitonic phases. And I was wondering if graphene has sort of an interesting excitonic response at the charge neutrality point.
Mm-hmm. Very good, very interesting. So first of all, graphene is not truly electron hole symmetric, okay? It's only when you look at very low energies in graphene itself that it looks particle hole symmetric. Once you include next neighbor Hoping terms, etc., the electronic structure of graphene is asymmetric. All that asymmetry at high energies falls down to lower energies when you make a Moiré superlattice, okay? So already at the single particle level, the electronic structure is not symmetric for electrons and holes in magic angle graphene. Separate from that, around the correlated insulator states, the electronic structure is already non-symmetric, okay? And in addition, then we have the possible complexity similar to what happens in the cuprates that is very different in doping with electrons and holes in the cuprates. Well, it might be that also in terms of correlations here is very different, the behavior when you dope with electrons and holes. So you have these three layers of, three possible reasons for why the system is not electron hole symmetric, starting with two, which are just at the level of single particle. Your second question, remind me, was about...
Is there any specific Moiré exciton features at the charge neutrality point in two-state graphene?
So some people think that, at charge neutrality, depending on conditions, there may be a gap or not, and there could be interesting excitonic physics at the charge neutrality point. I don't think anyone has evidence of it. People have looked at interesting interband transitions, because even though I didn't show you, the remote bands are much more dispersive near the gamma point, but they also flatten near the K points. So you have interesting optical transitions, flat band to flat band near the K points. And people have already some experimental evidence of very interesting interband plasmons and other optical responses there between the flat bands, okay? In terms of optics, I think the experiments are much more interesting so far in the transition metal dichalcogenides Moiré superstructure, where people have seen all kinds of interesting correlated insulator behavior, multi-insulators, generalized Wigner crystals, and excitonic correlation between excitons in various types of correlated Moiré heterostructures with transition metal dichalcogenides.
Right, thank you.
All right, the last question by Ranjani.
Hello. So so this is in context of another question which was asked about spin-orbit coupling in these systems. So, so what would be the effect of, say, a Rashba kind of a spin-orbit coupling? Because how do you induce it in such a Moiré heterostructure?
Mm-hmm. Very good. So we apply an electric field with our gate electrode, but that electric field in terms of Rashba spin-orbit coupling is very small, okay? Yeah. And graphene itself has a very, very small spin-orbit coupling, okay? Now, people are thinking about how to induce strong spin-orbit coupling in the system, right? Because it could add to the topological aspect, for example. One way that you can do that is by putting this magic angle graphene on top of an appropriate substrate. So bilayer graphene without twist angle and regular graphene both have been placed on top of, for example, transition metal dichalcogenides like WSE2 or molybdenum disulfide or tungsten disulfide. Those transition metal dichalcogenides have very large spin-orbit coupling, and they have seen, people have evidence that when you put graphene or graphene systems on top of those, you are able to induce a large spin-orbit coupling in the graphene itself, okay? So several groups are trying to do this with magic angle graphene also, okay? It's sort of an obvious thing to try. I'm not aware yet of a lot of reports where the spin-orbit coupling itself has been identified as having done something. Yeah, there's an interesting paper by the group of Stefan Perch at Caltech, where he put magic angle graphene on WSE2, and he saw that these effects of correlated insulators and superconductivity seems to change. Okay, So that might be due to spin-orbit coupling, or it might be due to screening due to the high dielectric constant of the system. It's not entirely known yet. So they're having effects, but I don't think people have seen direct effect of spin-orbit coupling in magic and graphene yet.
I see. I see. Thank you so much.
All right. Please join me in thanking Pablo again for this magnificent talk. And
Hi, can I do one question?
Well, if it's very brief, sure.
Right. Pablo, what is the order of magnitude of the electric field in the Morat ferroelectric?
In the Morat ferroelectricity,
Yes.
so I can tell you the displacement. Let me see. We have here, you can see here the polarization in 2D in units of 10 to the minus 12 coulombs per meter to the minus 1. Okay. We can induce, I don't have so this is essentially the question that you're asking. And we can induce, another way of looking at it is we can induce a charge density change in the graphene of the order of, by the way, you can see here, the voltage you apply by the bag divided by the distance. I guess this is also, in volts per nanometer, if you wanted that, that's, it's of the order of, 0.1 volts per nanometer, okay? That we are applying, to induce the switching, okay? So it's actually quite small. The change in density of the graphene that we can induce is of the order of 210 to the 11, okay? Which is another way of, looking at, so either, you can look at either of these three quantities.
All right, I will just remind everyone that the next IPC colloquium will be in 2 weeks by Jesse Thaler, so I recommend all join that as well. Thank you very much, everyone, and especially Pablo again. And good night or good morning, wherever you are.
Thank you all. Thank you very much.
Bye-bye.
Thank you all for this nice seminar.
Thank you.
מה אתה אומר?
יכול לסגור את המיקרופון בלפטופ ואני רוצה לראות...
סגור.
אוקיי, עכשיו אתה אומר משהו?
אני... Thank you everyone again, and see you in 2 weeks.
Okay, Serge, I will leave. Thank you, everyone. All right.
Bye-bye. And see you when all of this is over. All right. Bye-bye.
סרג', תודה רבה. לא שומע אותך.
ג'סי טלר, מוזמן על ידי?
מי הזמין אותה? שואל?
כן.
אני חושב... עיוני. למה אתה שואל?
טוב, נעשה את זה אופליין. טוב, נראה לי כדאי לה...